the extremophiles on Earth, which are very impressive. They can handle really high acidity levels and they can handle really dry places. They wouldn't stand a chance in the clouds of Venus. And so that's how bad it is. But it's not for us. We're used to thinking of places where aliens might be in terms of could we take it? And that's not how we should be thinking for many reasons. But one, it's not biologically plausible. Just because life can exist there is absolutely no reason to think we could exist there. There's only one place in the universe that is likely habitable for us, and it's here. There's no alternative because the symbiotic relationship between life and an atmosphere is very specific. We made this place habitable for us. It's not just going to happen somewhere else. And so the Venusian circumstances are still terrible for us, but it's not for us. It's for the Venusians, if they're there, which they probably aren't because it's not aliens until it's aliens. But for the Venusians, maybe it's fine. Maybe sulfuric acid is great. They use it a lot. It makes their life easier.
Hello, this is Robinson Earhart here with Pins the Podcat and the introduction to Robinson's podcast number 128. And this episode is with Clara Sousa-Silva, who is a quantum astrochemist and molecular astrophysicist in the physics department at Bard College. And Clara has, as far as my informal survey has been conducted so far, pretty much one of the coolest jobs there is, in that the focus of her work is geared toward finding alien life. And what's cooler than that? More particularly, though, Clara investigates the way that particular molecules interact with light so that we'll be able to identify them on exoplanets, which are planets that orbit a star outside of our solar system. And the reason that this will help us identify aliens is that the gases and other molecules detected on a planet give us pretty crucial information about its atmosphere and geology, and the presence of certain gases or compounds appears to be very, very highly improbable without the sort of complex chemistry that, so far as we know, cannot occur without life. And after talking about just what life is like as a quantum astrophysicist, though not as an alien, we turn to one particular molecule, and that's phosphine, which is what Clara did her dissertation working on and now works with today. And we look at the role that phosphine has or plays in the search for aliens. So Clara's website is linked to in the description. She is Dr. Phosphine on Twitter, and likes and comments and subscribes and reviews are all awesome. So if you've been listening on Spotify or Apple, reviews, even if you just press the 5 stars, or if you type great podcast, that is awesome and super, super helpful. So please do so if you've been listening. That would be great. Now, without any further ado, I hope that you enjoy this conversation as much as I totally enjoyed having it with Clara. Two of the other astrophysicists I've had on the show, Kevin Hang of LMU, who you might know, and then Chiara Mingarelli of Yale, they both told me that already as kids, they were totally obsessed with space. And Kevin, I know, wanted to be an astronaut. But I'm wondering if you're going to continue that trend. So how did you get into astrophysics in general, and then more particularly exoplanetary research?
Well, it doesn't surprise me at all that Chiara and Kevin have always wanted to be astronomers, and it also does not surprise me that Kevin wanted to be an astronaut. I very much did not want to be an astronaut. I still do not want to be an astronaut. I don't think we need to go into space, but I have kind of always wanted to be an astrophysicist. I was 12 when I decided, and it was very much a moment because I was watching a solar eclipse with my parents, and I didn't really know that we could tell what was going on. I thought people would know eclipses happen and why they happen, but it didn't occur to me we would know it so well we could predict every minute. And that was really shocking. And, my parents just knew that because they saw it in the newspaper, and they're both scientists, but not that kind of scientist. And I just thought it was unbelievable that we could predict to the second how things were going to move in space, and specifically that we could do it without going there. And that aspect of it, the reason I really wanted to be an astrophysicist and never wanted to be an astronaut, was because what I thought was really cool was knowing without going.
It's interesting to me already off the bat that you were attracted to the science, the astrophysics, by aesthetic considerations and the precision of the universe. Maybe we'll talk a bit about aesthetics when we get to phosphine. But the reason that I just find it interesting is it makes science such a human endeavor when, as outsiders, we think of it as almost like math, in that it's just about the technical aspects. But when I spoke with Kevin, another thing he said is he told me a bit about the distribution of astrophysicists within the discipline. And as he put it, there are sort of three categories. There are the instrument builders, there are the observers, and then there are the theoreticians. And I'm guessing you qualify as belonging to the theoretician camp.
Yes, I also think there's a lot of lab work that Kevin is ignoring here. People who make the measurements here for us to be able to predict what things we can't really measure on location will look like. So I would say there's four. Kevin is missing the lab people. People often miss the lab people. Ungrateful, fundamental work. But yes, I'm primarily a theoretician with a little of observing and a little of lab.
Lab work, yeah. And then I didn't ask him about this, though, but among the people who work on exoplanets in particular, since there are all sorts of phenomena for astrophysicists to chew on, but just beyond locating and cataloging the exoplanets, which I'm guessing would fall under the duties of the observers primarily, what are the various branches of research on the exoplanets themselves? If there is such a taxonomy or classification system, and then where does your work primarily fit in there?
Well, you're already touching on the problem of separating these categories completely. There's a huge overlap between them. And so the same applies when you look at, what can we know about exoplanets? So there are people looking at how do they form? And when they look at how they form, they have to look at how do they fit within a solar system? How did the star form? What that molecular cloud, was it the ashes of how many generations of planetary systems? Because that determines the composition of the dust that eventually leads to planets and stars. And so some people look at the formation. And then once you form, a lot of people look at, okay, depending on what you get, my interests are going to be either ice giants. What can we learn about those? Or gas giants like Jupiter and Saturn. What can we learn about those? And then you have the terrestrial planets like our Mars, Venus, Earth. And then you get the moon people who are also very important. And then if you consider studies into their atmospheres, even that ends up being very split. There are people who are doing incredible measurements and analyses now and theoretical models, and often those are the same people, of hot Jupiters. Those are Jupiter-sized planets that are very close to the star, and so they're very hot. This allows us to study the atmospheres very well because they're big and they're hot, but they're unlikely to be habitable. So even within the people who look at atmospheres, there's people doing the really important work of understanding the atmospheres of hot Jupiter, say, and then people closer to my interests who are looking at the atmospheres of smaller planets, or even the atmospheres of moons around those ice giants and gas giants. So we can't really afford to not talk to one another. But this gets us to my area of expertise and where most of my work goes, which is the atmospheres of places that could be habitable. And that includes very edge cases like, the plumes of Enceladus count as the atmospheres of places that could be habitable. Because what I'm really interested in is looking at these atmospheres and seeing if there's anything that could mean life. And I can't even isolate that because I need to be talking to the people who look at the origins of life on Earth, who look at it's called the exogenous delivery. So when like meteors and comets can provide the building blocks for life. And I have to talk to all the biochemists and even pharmaceutical experts here on Earth that can tell me what chemistry is possible or not, what complex molecules are stable, even outside carbon chemistry. And so I'm a good example of how you can't really categorize things very well. I can't even categorize my physics away from the chemistry and biology that I would also have to learn. And so, yes, these categories exist, but particularly when it comes to planetary sciences and the search for life, you have to blur them.
Mm-hmm. And this brings me, though, to the last sort of context-setting question I had, which is, what about the nature of your work on the atmospheres of these relatively small terrestrial planets makes you, in particular, a quantum astrophysicist? And I'm wondering if it has to do primarily with spectral readings and quanta of light and your work in the lab.
So I should have added that my work in the lab hasn't happened for many years. I just work with laboratory chemists who I'll say things like, I need UV readings of this molecule for this model, or I need some measurements of this molecule so I can calibrate my theoretical calculations. But the way the quantum comes into it, which is at first surprising because we're talking about things in such big scales. Even the smallest things I'm looking at are, moons. And so it's kind of cool how much quantum you need to study these giant things. And it's this bridging of scales that I really like. But it's a universal truth that molecules and atoms interact with light in a predictable way. Not deterministic, it's slightly probabilistic, and that's part of the quantum behavior, but it is something we can predict and test, and it will be true throughout the universe. The way water interacts with light in a lab on Earth is the same as the other side of the galaxy and galaxies beyond it. And that's really cool. And so we can trust that light and the pretty strict laws of chemistry and physics are the same everywhere, and that applies to quantum physics. And so when I try to figure out whether a molecule is somewhere, I'm looking at how it interacts with light here on Earth and trying to find those clues elsewhere. And that's all quantum behavior.
It's interesting that, I know there's a lot of talk about the crisis in physics, whether or not there really is in fact a crisis in physics. But my understanding is that one dimension of the potential crisis is the incompatibility of quantum theory with general relativity. But so it's nice that your work does in fact bridge the scales, as you put it, between the quantum and the macro.
And even within the quantum, I have to use relativistic corrections for my own quantum predictions because things move fast enough that you have to include those. And so even in the small scale, I do use relativistic corrections. And then the scale matching problem is another problem, but it's not like these different scales of physics are completely, only come to meet at the intersection.
Sure. And when you're saying that you need to make relativistic corrections because things move fast enough, are you referring to the redshift of distant planets moving away from us quickly that needs to be corrected?
No, electrons buzzing fast enough.
Okay, interesting. And then a lot of your research, starting at least with your dissertation, centers around a compound called phosphine. And I think that we should probably start with the very basics here, just what it is, since so few people, even though it's part of all of us, I understand, will have heard of it.
Yes, so phosphine is now something a lot of people have heard of and can spell, and that is definitely not what it was like during my PhD. My entire PhD was just answering questions no one had any intention of asking. And so things have changed in the last few years, but it is worth pointing out for anyone considering a PhD. I did the whole thing with no actual hope that anyone would ever care. And I must have the model here somewhere, so I'll find it. Yeah. Nestled in benzene, but here's my phosphine. So it's
I read some of your dissertation. It's very thorough.
Thank you. I thought I should put in the work. But yes, so it's deceptively simple. It's 4 atoms, 1 phosphorus and 3 hydrogens. So it's actually a very similar shape and a lot of similar quantum behavior to ammonia. But instead of a nitrogen, it's a phosphorus on top. And at the time, the reason I looked into phosphine was because we knew it was present in Saturn and Jupiter in quantities that were already a little surprising, because phosphine is simple in terms of construction, but it takes a lot to make it. The phosphorus atom and the hydrogen atoms don't really want to be together. There's always something that they would prefer to be attached to. And so it takes a very specific and quite extreme set of circumstances for phosphine to form. On Saturn and Jupiter, it's because the depths of those planets are insane places that are so hot and pressurized, and specifically hydrogen pressure, which you don't get that often, particularly not in habitable places. And so it's able to, just through sheer godlike power of these giant depths, depths of these giant planets, create phosphine. But phosphine, not only is it hard to make, it's easy to break. So it really kind of sucks as a molecule in like a March Madness thing. Phosphine would not make it very far. And it is hard to make, easy to break, but because Saturn and Jupiter are in the same places, they can dredge this, freshly made phosphine from its dead depths to the top. And it gets destroyed, but it gets transported faster than it gets destroyed. And so we see it. And by seeing it, we can make some pretty good guesses at how violent and from how deep these storms on Saturn and Jupiter are. So pretty cool as a marker for this kind of mechanical behavior, the dynamics of these planets. And it was kind of shocking that we didn't know how it interacted with light. So we didn't have the tools to detect it properly on other places. And that seemed ridiculous. This is a molecule with 4 atoms. Phosphorus is a limiting nutrient for life. Phosphorus and hydrogen are some of the most popular atoms in the universe, and yet we didn't have the tools to detect phosphine properly anywhere. Even on Earth, if there was a phosphine leak, couldn't detect it. And that was the sole motivation for my PhD. Can I, using quantum chemistry, develop a spectrum for phosphine? That's its kind of fingerprint when it interacts with light. And that's what I did. That was my entire PhD. There was no ulterior motive. I didn't think it would be useful for the search for life. I just thought this is fundamental knowledge we should have. And I did it. But because it was a molecule no one cared about, I could literally read every single paper that had ever been written about it that had been peer reviewed. And I did. Which sounds impressive, and it is, but it was definitely doable, which it's not for, if you want to do a PhD on methane, you're not going to read all the papers everyone's ever written about methane. And because I was able to read all the papers, I could find all sorts of weird stuff. Like there was someone who tried to propose phosphine as a plausible mechanism for fire-breathing dragons, because it is easily flammable and is associated with the decay of life. And so you could imagine a dragon like having a second stomach or something like cows, where stuff is decaying, producing phosphine, and then a little spark on the throat, and you could just get fire. And it was not even a terrible idea if we needed an explanation for a thing that doesn't exist. That's not bad. So this is a sort of like scraping the barrel level of research I did on phosphine. And when I did, I found out that the other things phosphine did, besides being a cute little thing on Jupiter and Saturn, is being a very much not cute little thing on Earth. Just an incredibly powerful and cruel molecule that kills everything in like multiple ways, some with delays. That smells awful. There was a technical report that described it smelling like the rancid diapers of the spawn of Satan. And so it's just this like garlicky, fishy smell of death. But there's very few reports because people who smell it don't live. And so it's just this cute thing that, survives barely on these planets. And then here is like, and it's just kills. And so I was kind of fascinated by this duality of phosphine as this apparently simple molecule that is barely there anywhere. And then when it is, it's so deadly. And that was my first foray into what phosphine is capable of.
I like that somebody investigated whether or not it was a plausible mechanism for dragons to breathe fire, because you mentioned if we needed an explanation for something that don't exist, fiction writers often like having explanations for their creatures that don't exist. So that's good fodder for the writers. But so despite phosphine being, in your elegant terminology, a sucky, difficult molecule, at least in how difficult it is to form, since we already mentioned with regard to your attraction to the solar eclipse, aesthetics does play a role in science. And I'm not sure that non-scientists totally appreciate this, but do you find the phosphine molecule itself to be beautiful or special in some other way? I mean, one thing that just immediately comes to mind for me upon looking at the phosphine molecule is that it is kind of the most basic shape of the pyramid, which you might have said, which for some philosophers that could be construed as like a natural kind.
Yes, but you would have to be ignoring all the invisible forces that I often end up simulating and then seeing, because it is deceptive how simple it is. And I know I can imagine how hard it is for these bonds to make. They don't seem simple to me. And so there is this part of the aesthetics of what I do is trying to figure out how to visualize the things that I couldn't even possibly conceive of. A lot of them are not even deterministic, and so it's really hard to do. And phosphine does have a very pretty spectrum. When I first simulated it, Jonathan Tennyson, my supervisor, who's an excellent quantum chemist, he said, "Oh wow, that's a textbook spectrum." And he's right. You could teach quantum chemistry with phosphine, and I do, because it does have a beautiful, simple spectrum that is very easy to distinguish from other molecules. And so when you're looking at the light from an atmosphere, you have features from, carbon dioxide, water, methane, whatever is present there. And a lot of these features overlap each other. And phosphine kind of comes off the side because this bond between hydrogen and phosphorus is so rare and so spectrally powerful that you can use it on its own to detect phosphine amongst a crowd of much more popular molecules. And so phosphine is very pretty in that sense. The way it interacts with light is not unique, but it's certainly very distinguishable. But interestingly, I did collaborate with a composer, David Ibet, who kind of heard me talk about these vibrations of these molecules and the frequency with where those vibrations occur, and the intensity with which these vibrations occur is what makes the quantum spectrum of a molecule. And him being a musician was like, vibrations, frequencies, intensity, that's just music. And so he managed to sonify the spectrum of phosphine, and is really beautiful. And it's really nice to hear kind of phosphine. I will never be able to smell phosphine and talk about it. I will never be able to see phosphine unless it's dying, igniting. But I can now hear phosphine. He transposed it to a cello solo piece. And I think one of the rehearsals is up on YouTube. So if you Google cello phosphine, I'm fairly certain there's only one hit. If there's more, that's really cool. And that would be Minjing Chung, I think, rehearsing that piece. So not an official audio, but you can kind of tell that it's beautiful. And it's really nice to know that this deceptively simple and known to be horrific molecule can sound really ethereal and pleasant.
Well, at least phosphine has been captured literarily, though, as the like the diapers of Satan's spawn. So at least you have that. But okay, so you find the spectrum attractive, and your advisor, like you said, Jonathan Tennyson, described it as a textbook spectrum. Is it possible to explain just what it looks like and what makes it textbook without an image? Or is that just too difficult to attempt?
I can try. And so the spectrum of a molecule is a series of peaks at different wavelengths. So if you can imagine a rainbow, each molecule will absorb or emit only some colors of that rainbow. And that rainbow includes ultraviolet and infrared light. And the spacing and the intensity with which these absorption happen forms a spectrum. And the spacing is determined by how a molecule vibrates. So kind of how fast it bends and stretches, in this case, dissociated, and how it rotates. And sometimes how the electrons jump within this molecule. So if it just rotates, this is called a rotational spectrum. If it vibrates and rotates, it's called a rho vibrational spectrum. And if it rotates, vibrates, and has electronic excitations, it's called a rho vibronic spectrum. But when you look at the spacing in these rho vibrational spectrum, a lot of molecules have a variance of spacings and intensities that depends on many, many factors. But if you're teaching it and you only want to explain kind of the first, most important kind of three factors, how it's rotating, how it's vibrating, how the electrons are getting excited, phosphine is pretty good at showing kind of clean spacings, a growth and a decrease of intensity at the right points. We call them branches. It has very neat branches of the spectra. And so when you're teaching, it's easy to point to them and say, this is because it's rotating like this. This is because it's vibrating like this. And with other molecules, you would have to invoke much more complicated behavior of movement between energy levels. And so that's what makes it textbook without drawing a picture. It is almost helpful molecule in terms in didactic terms.
Okay. Well, this has all been great. And now that we've got a lot of background on phosphine itself, I think we ought to turn to phosphine's relevance to the search for extraterrestrial life. But first, in doing so, we should start with Earth. And so how is phosphine produced by by life on Earth? And what sort of life is it associated with? Because I gather that this is very significant for its relationship to the search for extraterrestrial life on exoplanets.
Indeed. Yes, I mentioned when I first started looking into phosphine, it was really the corners of human knowledge beyond kind of Jupiter and Saturn. And so people had already made several mentions of phosphine being found near things on Earth that contain life. So people are very cautious at associating a particular molecule with life, and they should be. We have now got things like petri dishes with bacteria who then phosphine appears. So it's a pretty safe relationship. But we first knew how phosphine killed before we knew how phosphine played along with life. And so the two are very much heavily related. Phosphine kills by kind of messing with oxygen metabolism, which we do all the time. And everything we like and love uses oxygen metabolism. And phosphine really, really does a number on that process. And so that's what makes it an effective killer. But that's also what makes it completely harmless to life that doesn't metabolize oxygen. Now on Earth, this life, anaerobic life, is very much in the shadows and really poorly studied. So I think if you break down like the amount of money or number of kind of PhD theses done on all life on Earth, and you break it down by life that it's aerobic, so uses oxygen, and life that avoids oxygen, anaerobic, it is really disproportionate. There's a lot less of that life, but even accounting for that, we really don't study it. That's because it's always in horrible places. Anaerobic life is in swamps, at the bottom of lakes. It is in everyone's butts. Like, these are not places people are rushing to go and look at. And so we avoid it. But these are rich worlds. Your intestines and that of every animal is a world in itself, with many species working together or not, but a rich ecosystem that just doesn't care for oxygen. In fact, when oxygen comes in, it's deadly. And in these places, phosphine is produced. So you mentioned at the beginning of our conversation that you had phosphine within you, and it's within you, but kind of on the outside. It's in your intestines, where that's a whole different world. There's a biome there. And that phosphine is not in quantities that can kill you, but it's certainly not pleasant. But that connection is what made me think, why would we dismiss this world that we have within our world, this anaerobic world? Most planets we have found in the solar system and beyond are not oxygen rich. And so our search for life cannot be limited to life that likes oxygen, or we are very likely to just miss it altogether. It would be lovely to find peers, alien life that we could just hang out with. But the odds of that are very slim. And so phosphine and other molecules produced by anaerobic life seem like a really good starting point, because this is a second data point on Earth. People often complain in the search for life, we really only have one data point, but that's not true. Even on modern Earth, we have these 2 data points. And then there's the whole history of life on Earth to give us more. And so it was this concept of phosphine, a very difficult molecule to create. So it has very few false positives for life, because it's not likely to just happen spontaneously and hang around. But on Earth is only produced by life with enormous effort. Sometimes so you can use it as a biological weapon, and sometimes by anaerobic life that doesn't mind having it around, though it is still a mystery why it is making phosphine. And this made me think I should look for it elsewhere. And I did not think I would find it. I very much thought I would die. Well, I was hoping I would retire and then someone would find it somewhere. That was my hope. And then I would be like, in my chaise longue and someone would contact me for my help. But I didn't think I would have to work actively on phosphine anywhere. I didn't expect to find it. So that was just a hypothetical that then turned out to be very real.
So you mentioned that oxygen is vital in our atmosphere for much of the life that our planet sustains, and that if we found it on other planets, that would be a prima facie reason for thinking life might be there, at least in so much as extraterrestrial life might resemble human life, which is, a major assumption. But I also gather that oxygen might also occur quite naturally in a place with no life at all because of maybe geological features, something like this. And you already mentioned that gaseous planets like Saturn or Jupiter, which at their core have these godlike forces, can produce phosphine. But is it on the smaller terrestrial planets that you're interested in studying, is it also likely that, or possible that we would find phosphine when there is no life present there?
Yes, it is just very hard for that phosphine to persist. And so in Jupiter and Saturn, you can make phosphine in quite large quantities because they're big places, and then you can continue to produce it. On Earth, the only things capable of kind of putting in the work to make a molecule like phosphine that is so hard to make are things like industrial labs, a sign of life, anaerobic life, a sign of life, or sometimes in very small quantities, you can get things like lightning or volcanoes, so really intense short bursts of energy. You can also make phosphine. But then on Earth, it has about a 28-hour lifetime. And so within a day-ish, phosphine is gone again. And so you need to constantly be supplying it to be able to detect it. And so when I was modeling all of these potential planets that could have phosphine being produced, I was only able to detect that phosphine if it was constantly being replenished. And if it was made in quantities that volcanoes and lightning just can't make, even if there's a lot of volcanic activity and a lot of lightning. And so it's not that phosphine can only be made by life, but any detectable amounts of phosphine can only be made by life, at least as far as we know. The case of Venus has been a really interesting one, which we can talk about if you'd like, because Venus is quite an intense place. It's not like Mars or Earth or other terrestrial planets where weird stuff can be happening, but it's not constantly trying to kill you. But Venus is a really, it's somewhere between a placid Mars where nothing happens and a Jupiter-like planet where there's so much happening. And so Venus is a really good edge case where there could be much more volcanic activity than we think. And there could be some weird stuff happening in the clouds and just some geochemistry we don't understand that could maybe make enough phosphine for us to detect it. And even in a place like that, we're still really struggling to find a non-biological production mechanism because it's really hard to make phosphine. It's not a molecule that wants to be made.
Yeah, and I would like to get to Venus in a bit, but there are still some sorts of, I guess I'll refer to them as preliminary issues that I'd like to touch on first. And one, so the anaerobic life associated with phosphine on Earth, as you mentioned, is microbial. And does this mean that, and again, in so much as terrestrial life is the model that really constrains what we expect to find on exoplanets, that we aren't expecting to find intelligent life on planets where we detect large quantities of phosphine, or we aren't expecting the alien invaders to smell like Satan's diapers?
I'm not expecting intelligent life at all. I think life is inevitable, but intelligent life is not something I put any stock into. The odds are at least vanishingly small. And so I don't look for intelligent life. I wouldn't miss it, if I was looking. Intelligent life tends to be a little louder than the microbes in the grass. But I am not particularly working particularly hard at looking for intelligent life. Life itself can come in a variety of complexities. On Earth, it's true that anaerobic life is not particularly complex, but it hasn't really had the chance. We won. We, oxygen-loving life, have won. We've taken over Earth. Earth used to be very friendly to anaerobic life, but we terraformed it in our image. We changed our atmosphere to be filled with oxygen. And life did that. And when it did that, it was the biggest massacre. It killed everything that couldn't handle an oxygen-rich atmosphere. And so we are the survivors of that particular war. And so I don't want us to make the mistake of thinking that history is inevitable. We won. We have an oxygen-rich environment, and the life that thrives in it is oxygen-rich. But it's not like anaerobic life has a fighting chance on this planet. That doesn't mean on other planets it wouldn't have. The limits to complexity, depending on your biochemical choices and the environment you're in, are likely different. But we don't know. We don't know how far anaerobic life could have gone had we not ruined its planet.
Yeah, so this is something that I was really curious about. So you're of the opinion that there is microbial life out there. It is perhaps abundant, but you're more agnostic about the existence of intelligent life because if it is out there, there'd have to be such drastically smaller quantities, or the proportion of it to unintelligent life would be so small. The reason that I think that this is really important is that, so I've spoken with Avi Loeb on the podcast, and I'm sure, if you just look at his CV, he's a terrifically accomplished astrophysicist, and he's done some really great work. But I think that his research on extraterrestrial life is quite biased, probably, by his extreme conviction that there is lots of intelligent life out there, which, granted, I'm not an astrophysicist. His conviction seems to be overblown and ill-founded, but this consequently results in his seeing aliens where I'm not sure the evidence permits it. And I don't want to assume that you have these same prejudices, but it's good to keep in mind, for me at least, what your credence is in the existence of alien life and its distribution throughout the universe, because that's going to affect how you interpret your data, whether or not you want it to, really.
Yeah, Avi is an interesting case because, yes, he's an excellent astrophysicist in many fields that aren't astrobiology. In astrobiology, there's a field he entered into alone almost. I have a lot of astrobiological work that I do, and it's very collaborative, and it is very hard to do this sort of work in isolation. But Avi has very strong feelings about aliens in the traditional X-Files sense, which is very much at odds with the rest of the expert community. His intent is to find it, and I would love that too. I had SETI on my desktop when I was little. I've put in the hours. I think that it's really appealing to the public, the search for alien intelligence. And it is very easy as a scientist who works in a field that close to it, like me. It is very easy to get carried away with what the people want to hear. We would all love to find perfectly spherical debris from alien spacecraft that just came in. That would be cool. I think it would be cool. It just didn't happen. The Occam's razor situation here is so far from where we're at. And it's a really important thing in science, and it's a vital thing in astrobiology to never presume aliens. That's the rule. It is never aliens until you have literally excluded everything else. And even then, what you say is, there's still probably things I don't know that are still more likely than aliens. When we were trying to figure out what could possibly cause phosphine on Venus, we tried everything that was obvious, and then we tried everything that was not obvious. And then we were like almost drunkenly thinking of like, what if there was bismuth snow that hit a tectonic plate, that a plasma... That's the reasonable thing to do. To think of the most extreme geochemical explanation you can possibly think of and not presume it's aliens. And so it is, for me, unthinkable to approach any problem in astrobiology with a presumption that it's life. And a presumption that it's intelligent life, that has an even higher barrier to entry that seemingly is not a barrier at all to Avi. It's just an open gate with a red carpet. Mm-hmm. And that's the distinction.
What I think you're describing with the bismuth snow is the normative ideal in science of trying to falsify your hypothesis rather than seeking to prove it. And just to clarify my own thoughts on Avi, I think he's a great guy. He's really nice. He's clearly extremely intelligent, and I'm glad that he's working on this. And I'm very interested in continuing to hear about it, like his dredging right now of the
spheres,
sand, for these little microspheres that he thinks are of alien origin. But I can entirely understand why many astrophysicists kind of bristle at his name, because they think he's tarnishing the rigor of science by not really following this ideal falsification protocol.
And it's hard to be respected as someone who studies alien life. I'm always struggling to be taken seriously. I'm a woman in science who is studying aliens. This is not easy to be taken seriously. And so much of my work is exhausting because I need to make sure that I can validate the things I say and I can caveat things correctly. And I spent, hours, weeks, months, years of my life putting all this work into being really careful to have Avi come in and be like, aliens! And so I love Avi. He's wonderful in many ways, and I've seen him protect junior scientists. I wish he was more careful, much, much more careful, because it has consequences for people like me.
Yeah. Well, for what it's worth, I mean, you're an excellent communicator, and I think for anybody listening, it's quite clear that you're a very serious scientist.
Well, thank you.
So that's great.
Even as I talk about dragon breathing.
Yeah, well, that's still important. Science is still a human endeavor, and
a speculative one.
Yes, a speculative one. So something else that I wanted to ask about phosphine, and I promise we will get to Venus.
We don't have to. We can stay on phosphine the whole time. I don't mind.
Okay, but what I'm curious is, are there ways in which phosphine might be a useful molecule for extraterrestrial life in a way that terrestrial life hasn't harnessed it? So I guess maybe we could start, though you've touched on it a bit, with just the ways in which terrestrial life. So I think there are these worms, maybe by hydrothermic vents, that make use of phosphine, but how explicitly it's used on Earth. And because I saw some interesting thoughts you had about how aliens might use it. So
on Earth, we still don't know why life makes phosphine. We know that it does, but it's just robust circumstantial evidence, which is true actually for most molecules we consider biological molecules. It's much easier to, kind of watch a biological kind of small petri dish with some biology on it and then watch what molecules it produces. It's much easier to say, oh, it produced those molecules, than it is to figure out what is the enzymatic pathway, like what is the actual chemical mechanism that made it. And so this is not surprising, but I think for some people it's like, wait, you don't even know why they're making phosphine? Maybe they're not making phosphine. Maybe it was just there. And that's not true. So we do know. But why is an incredible question, because it is really, really, really hard to make. And so the best explanation we've got is that there are other molecules that are really, really hard to make, that the universe doesn't just spontaneously make easily, like isoprene, for example. And these molecules, do I have isoprene? I do. Wait. And isoprene is
these models are handy.
A much more fun model than phosphine. Look at this. Come on. Isoprene, deceptively simple because it's only carbons and hydrogen, but you can see it's more complex, is produced by trees at an enormous cost, a sacrifice, which is the theme here. The universe doesn't sacrifice, but life does. And when life on Earth makes molecules at a huge cost, when it sacrifices energy to make these molecules, it's usually for a pretty complex behavior. In the case of isoprene is to signal. So trees use it to signal to each other danger. And it gets destroyed very quickly and creates a blue haze. It's why the Rockies are blue, why you see a blue haze in the mountains. That's isoprene being destroyed. But the reason this makes sense is if you're trying to communicate with a molecule, you don't want to make a molecule that could accidentally be there already, because then your communication is flawed. And so you're willing to sacrifice, to put in the work to make a molecule that could be a clear form of communication. So that's the case of isoprene, and that could be the case for phosphine as well. Phosphorus is also a limiting nutrient for life. So a lot of life puts a lot of work into getting phosphorus compounds. And so people have suggested that it could be part of like a bartering economy in the oceans, which is really cool, but a theory with a lot of problems. But the most obvious way in which life is willing to sacrifice to produce something really weird is because it's a good weapon. And so we already know phosphine kills. So it could be very well that anaerobic life is willing to make phosphine to protect itself from the oxygen-loving attacks of life that we like and smells nice. And so defense, attack, communication, or some economy are good explanations for why you would want to make phosphine, but we still don't know why.
So on Earth, at least, just to summarize a little bit. So on Earth, at least, so far as we know, phosphine could just be a byproduct like oxygen and photosynthesis and not necessarily be useful, rather than something that's produced and used like ATP or isoprene. But phosphine may be functional like isoprene. And
it kind of has to be functional because it's costly. So byproducts are not costly. Byproducts are usually an easy way to get rid of something. No one's going to sweat out phosphine for fun. It's expensive to make. And so molecules that require a sacrifice are usually involved with complex things rather than byproducts of other interesting actions. And that's kind of why it's also a good sign of life, because other molecules like water or methane, lovely molecules, definitely produced biologically in large quantities. So they're biosignatures in that sense. But they're produced in 1,000 other ways on a terrestrial planet or a habitable moon. It's not hard to make methane. And so life makes it and not life makes it. With phosphine, very little not life will put in the work to make it.
Okay. Thanks for clarifying that. And I have one more sort of, I guess, line of questioning before we get to Venus. And one of the reasons that I want to go through all of this does go back to the Avi Loeb issue. Is I just want to make sure how clear, like, hard science is going into this, and you're not just seeing aliens everywhere, basically. But what I'm wondering is what daily work on these problems looks like, because I think that's very interesting for non-scientists. Because I'm wondering, is it a lot of time spent in front of a chalkboard, or the kind of fantasy lay people have of scientists with beakers full of colorful liquid, or tinkering around with computer code, modeling different situations? Like, what sort of thing, other than the pleasure of having conversations with people like me on a workday, are you doing related to these problems?
So no beakers, but yes, it's a lot of modeling. So a lot of modeling and a lot of emails and video chats with lab people who do have beakers, just not phosphine. And the main game is all in the service of not missing life if you're looking at it. And so the game is, you have this light from a planet, and that light is composed of all the molecules that are in there. And the game is saying, okay, which of those molecules shouldn't be there? If they shouldn't be there, what are the explanations? And are we even sure we got it right? Because the signals from one molecule can look like the signals from another. And so the step is, what molecule could cause a signal? And that's really hard. And so it's a lot of looking at observations, a lot of injecting fake noise into it to see if it goes away. And if you could assign a signal to a molecule, you go, okay, what is that molecule doing there? And a lot of times you can say, well, we know the star and we know other molecules, so it could just be photochemistry. The light hits it, it breaks it, now you have products, and these become reactants for new molecules. We can explain it away. This is what happens. There's light, there's a planet, you get this molecule. That's not surprising. Or let's say in the Avi Loeb extreme, we go, that signal, I know that signal, that's CFCs. CFCs, not even Jupiter and Saturn can make. Those are molecules that only a intelligent civilization with a death wish would make.
Chlorofluorocarbon?
Exactly. And so these outputs from industrial activity, like CFCs, would be very quickly you would be like, well, I think there's life there. Probably not for long. CFCs are not great for a planet, but there's life, there's intelligent life, and they're probably going to kill each other. And that's incredible. So you go from going, oh, there's a molecule, that signal is definitely that molecule. Maybe they have oceans, good for them. Or there's a molecule that could only be in life. Most molecules fall somewhere in between these two. Phosphine and isoprene are closer to the CFCs than to the molecules that just happen naturally in the universe, but they're not there. There's still explanations for them that don't involve life. And so most of my work is thinking of this entire list of molecules between water and CFCs. And that list is 16,367 molecules. And so I spend all of my time, when not talking to people like you, figuring out what does that signal look like? Could we get it wrong if we saw it? And if we see it, what could it mean? And it takes about half a decade to study each one of these molecules. So you can see how these numbers are not in my favor. But that's what I do every day. I try to chip away at that list.
Yeah, my understanding is that this methodology has currently got us in a really tight bottleneck because there are far more gases, as you've just indicated, out there that could be indicative of life than we currently have the signatures to detect. And it took you 5 years just to get one of them.
And that's to get the signature. It took me many, many more years to then figure out if we did see it, phosphine in this case, what would it mean? And to do that for every other molecule is just completely overwhelming. I can't train people fast enough, and I don't have the money to train people fast enough. And so it's easy to let it stress you out. I'm very zen about it because it's so impossible a problem that there's no hope I could solve it. And that's a relief.
But I have seen, though, which is very cool, that you're doing a ton of work getting young people involved in astronomy and having them do real research, which is quite laudable, if I don't say so myself.
Thank you. A lot of astrophysics feels very selfish, you know. I could have chosen many sciences, but I chose the one of me, you know, looking into the skies, contributing nothing to humanity. And so the very least I can do is train the next generation.
Mm-hmm. And so I have a couple more questions about the modeling. So again, just to give the non-astrophysicists like me a better idea of what it means to say you're modeling something. So what goes into modeling a planet's environment on a computer? What does this look like? Because it's not like you're making a playable video game environment, which is what I think people might intuitively think of.
We should put some work into getting like actual visuals to the things we're doing, because it would be so cool. But we barely have the GPUs to run things we want to run without trying to actually
huge computer power.
Huge computer power. I mean, when I was doing just the phosphine spectra, so just one molecule, not the whole atmosphere. I remember my temporary files that I had to move around were 11 terabytes, just of my temp files, not the actual outputs or my inputs. Those are just things that I had to like shuffle along as I calculated these giant matrices that would break computers everywhere. I would have to time my calculations to the average length of time that electricity doesn't get cut off. You know, so it was like any calculation took longer than 3 months to run, I just couldn't do because I knew the odds that something would go off within those 3 months, and then you would have to start from the beginning. And that's for one molecule. When we're modeling a planet, we have to cheat. You know, we have to really simplify things. And so we presume a certain production of molecules at a surface, and sometimes we can like sprinkle some a little higher up. And then we have the code input every type of reaction between every molecule at that temperature and pressure. And for every bit of the atmosphere, which we cut into these like envelopes, you can imagine like spherical envelopes. And for each section of the envelope, we figure out, okay, what would these reactions lead to at this temperature and pressure with this much light making it from the top? And then we do this for every layer, and we let the layers interact. And then we see, okay, if you observe the third most layer from space, what would that look like? And that's kind of the simple explanation to what we do. But this is a problem that grows very quickly, as you can imagine. When you put more molecules in, more different types of light from the star, winds, convection cells, production rates that vary between day and night, the volcanism, lightning, it becomes a really intractable problem to simulate a planet, as it should be. You know, it's a really complex place.
Mm-hmm. Right. Yeah. So, given the computer power constraints and the fact that you can't completely model a system with anything smaller than the system itself, which for a planet, the amount of information involved is just absurd. No computer obviously could handle it. So just the last thing, are there any relevant variables that play a part in your models beyond some of those that you mentioned, like temperature and pressure, or light because of its role in breaking down phosphine, or lightning and volcanic activity? Or are there any other major ones?
The reaction rates. And I say major ones because, you need to know how molecules created and destructed. Say if I find a molecule, if there are many ways of it being produced within the photochemistry and the geochemistry of that environment, then we'll never be able to pinpoint it as a production, an output of life. And so for that, we need to know reaction rates. And on Earth, we know very few, and only for the molecules on Earth. And so whenever we're simulating a planet, 100% of the time, we have to just make up reaction rates because we don't know them. No one's measured them. And that can really change what the output of this model is, which is crucial if we're trying to then observe a planet and say, well, our model of that planet matches the observation, so we must be right. It's really easy to get it wrong and to miss it.
Okay. Well, now without any further ado, we can get to Venus. So in 2020 or so, there was this serious discussion of which you were a part, along with some other very notable astrophysicists like Clara Seeger at MIT, about whether or not a potential discovery of phosphine in the atmosphere of Venus indicated that there may have been life there. So just in general, you mentioned a little bit about it, but what was the story here? And then what's the status of the investigation into life on Venus now?
So when I first joined MIT to work with Clara Seeger, I had already been doing all this work on phosphine as my PhD. I just didn't think it would be very useful beyond my PhD. But I had hopes from my investigation into anaerobic life that it was a potential biosignature. At the time, Sarah really didn't think it was. She had worked with some very, very good biochemists who were like, phosphine is just not a good molecule for life. But then we ended up working together, and specifically these biologists, biochemists, Janusz Petkowski and William Baines, who are excellent scientists. And me and the two of them kind of figured out that phosphine was a really good biosignature. And we published that paper, kind of defining the constraints that would make phosphine a good sign of life. Separately, completely independently, Jane Greaves, who's at Cardiff, who studied lots of solar system bodies, not with any intention of finding life, thought to look for phosphine on Venus. And when she looked with two separate observations, it seemed like phosphine would be present there. Now, she's doing these observations, and that's her expertise. But of course, she didn't do a PhD on phosphine and didn't really knew it was weird and unexpected, but didn't know what it could mean. And so Jane reached out to me because by then I had spent 6 years telling bored audiences all about how cool phosphine was. And they're like, phos what? But some heard it and were talking to Jane. And when Jane mentioned phosphine, said, you should talk to Clara. She's Dr. Phosphine. And so
your Twitter handle, for those who are wondering.
It is my Twitter handle. And this came out of when I was at conferences as a PhD student. People would come and say, hey, are you Miss Phosphine? And I was like, damn, I am. But one day I will be Dr. Phosphine. And so it was. But Jane got in touch with me and was like, I think I found phosphine on Venus. It's weird, right? I think it's weird. And I had to reply very quickly, being like, yes, it's very weird. Give me a minute. And so I went to Sarah and I was like, this is going to be a big deal. If it's right, probably not right, right? And Sarah's like, it's probably not right. We get weird emails all the time. And then it was me and Janusz and I think William as well, who really thought, okay, it's probably not real, but if it's real and we're right about it being a good sign of life, it's a really big deal. And so that's how that collaboration started, with a lot of disbelief. And not all of us now believe that phosphine is the best explanation for the signal that we see on Venus. It is basically something weird, for sure, happening on Venus. And it's been a way of realizing quite how little we know about Venus and how embarrassing that is. Venus is a incredible place that is right next door. And we're putting so much work and so much money and so much energy into studying distant exoplanets, but we basically ignored this rich laboratory for the study of how a planet can behave and how an atmosphere can be and how life could maybe be within it. And we're wasting this opportunity. And so that's the real lesson in the Venus story. Yes, the signal may be phosphine. If so, it is a really big deal because, as I explained before, it is really hard to explain the presence of phosphine on Venus. That is true, a fact. It is extremely hard to explain the presence of phosphine. There are ways of explaining phosphine, and there are ways of interpreting the signal in which it's not phosphine at all. But if it is indeed phosphine, William led this work, and he is very good at figuring out the negatives. And this is, I think, a paper that's like 140 pages long. And that's because we cut a lot of things because they were too crazy. Of just trying to explain phosphine in any way that didn't involve life. And we failed, and people on Twitter and in papers published lots of alternatives. We tried them all. We cannot explain phosphine on Venus. But it may not be there. And if it is there, it is still the most likely thing that we just missed some exotic geochemistry. But if we didn't, and it is life, it is really cool. So I'm really glad I answered Jane.
I'm wondering if you can dispel a little bit of confusion that I have, which is, in preparing for our conversation, I read a number of different articles and papers just about this topic. And it looked to me like initially there were some problems with interpreting the data, the spectral readings, and it at first looked like there was a much higher concentration of phosphine in the atmosphere than there in fact was. Is this the case? And maybe was it the case, or is it the case that if the prior readings had held and there was a much higher concentration of phosphine in the atmosphere, there wouldn't have been as much controversy or questioning about whether the signal is in fact phosphine, and you would have a higher credence in the proposition that there is life on Venus than you do now, where now it's something of a question.
A totally fair question. And so I think we went from estimating 20 parts per billion to like 5 to 7 parts per billion when the data was recalibrated. Neither can be explained abiotically. And so all our explanations for how we could make phosphine without life were still many orders of magnitude below either of these readings. And so having a higher reading means it's easier to make follow-up observations. So that would still kind of have consequences for both the presence of life potentially and our interpretation of any signals it may be creating. So more abundance is better, but we're still talking parts per billion here. We're expecting still very small amounts of phosphine and still amounts that we can't fathom how you would make without life. And so in that sense, no, it doesn't make any difference. But it goes to show that this is all being done at the very edge of instrument capabilities. And that is a really noisy place. And that's, I think, the crux of the problem. Phosphine is a great example of what will happen with any potential detection of life. It will always be done at the edge of instrument capabilities because life is not loud and we're just barely able to see these potentially habitable places. And this place is noisy and delicate and very vulnerable to multiple interpretations. And so my main goal since the Venus story came out has been trying to figure out a way of talking to the public and even my peers about how to correctly transmit the inevitable uncertainty that the detection of life will have. We will not find aliens, in a burst of prime numbers through the sky. That would be really good and I would love it, but that is not how we will find life. We will find life that is not very loud with instruments that are very new, and it's going to be really hard to be sure. And that's okay. That's the truth of the path to detecting life. But I think people always hope for a smoking gun, and we're not going to get one. And phosphine on Venus is a great example of that story, because let's say there is phosphine on Venus, and let's say that it is life producing it. even if that is true, it is still really hard to detect that phosphine, never mind being sure the life is is the one producing it. And so I am very thankful for the end of the decade missions that will look at Venus more closely. But this is a lesson that we will have to learn now, because yes, we can send probes to Venus, but if we find a sign of life on an exoplanet, we can't send probes to check. And so we need to figure out how to tell the truth from far away.
Mm-hmm. And so I still have a cluster of questions. And Venus is, despite being a terrestrial planet like Mars or Earth, it is very, very, very different from Earth. So I think that the surface temperatures average something like 800 degrees. There's Fahrenheit. Sorry, I'm biased. That it's constantly raining sulfuric acid that melts probes that land within like a couple of minutes. So the life there has to be quite different still from our life, since no Earth life would survive in this sort of atmosphere. Now, something I read is that and again, registering our hesitation about saying that there is life, because one, granted the speculation about just what the data could mean, but also it's not aliens until it's aliens. Let's just assume that there's life. We're going to.
It's not aliens until it's aliens, but let's just say it's aliens.
Yes, let's just say it's aliens for the purposes of this conversation. One thing I read is that these aliens might be living in the clouds, because maybe 30 miles or so from the outermost reaches of Venus's atmosphere, there are clouds that don't have all of this sulfuric acid, and then they also are at temperatures of like 80 degrees Fahrenheit, something to this effect. Is that how you think about what the life might be on Venus? Something living in the clouds?
Partially. So it has to be in the clouds if it's there. The surface is not just uninhabitable for life as we know it, or we might think we know it. It's kind of uninhabitable for the sort of complex chemistry that could be any life. It just destroys chemistry. It is just a bad, bad place. But the clouds are better, but not as good as you made them sound. So yes, the temperature is a warm summer day. The pressure is a totally reasonable, kind of similar to Earth's surface. So in many ways, way nicer than Mars. So although you made Mars and Earth seem like the easy ones, Mars is not a good place for life anywhere. At least Venus has decent clouds. I say decent because pressure and temperature are really important. As I mentioned, you kind of need them to be reasonable if you want chemistry to succeed and biochemistry to succeed. But it does still have a lot of sulfuric acid. You can think of the sulfuric acid on Venus, not so much as it rains sulfuric acid, but what isn't rain isn't sulfuric acid. On Venus, it's all sulfuric acid. It's so bad. It's more like a little bit of water diluted into sulfuric acid rather than the way we're used to thinking of acidity. It's just a really still pretty intense place in terms of acidity, and importantly, in terms of how little water there is. So it's very acidic and very dry, kind of drier than anywhere else on Earth where there's life. And so the extremophiles on Earth, which are very impressive, they can handle really high acidity levels, and they can handle really dry places. They wouldn't stand a chance in the clouds of Venus. And so that's how bad it is. But it's not for us. We're used to thinking of places where aliens might be in terms of like, could we take it? And that's not how we should be thinking for many reasons. But one, it's not biologically plausible. Just because life can exist there, there is absolutely no reason to think we could exist there. There's only one place in the universe that is likely habitable for us, and it's here. There's no alternative, because the symbiotic relationship between life and an atmosphere is very specific. We made this place habitable for us. It's not just going to happen somewhere else. And so the Venusian circumstances are still terrible for us, but it's not for us. It's for the Venusians, if they're there, which they probably aren't, because it's not aliens until it's aliens. But for the Venusians, maybe it's fine. Maybe sulfuric acid is great. They use it a lot. It makes their life easier.
Mm-hmm. Yeah, and I think this idea might sound insane to most people in the first place. I mean, aliens in the clouds, but one, like you mentioned, we probably have a sort of anthropomorphic bias, and we're thinking about, okay, aliens as macroscopic animal aliens in the clouds. But one, that's not what we're saying. And two, there's already microbial life in our clouds on Earth. So it's not that insane in that sense. But the next thing I'm wondering is, granted that you mentioned that this research is all being done already at the edge of instrument capabilities. And as I said, it's very difficult to send probes into Venus because of the sulfuric acid. So what then are the next steps for investigating this hypothesis, particularly as it relates to Venus and not other exoplanets?
So Venus is a perfect place for us to find a potential sign of life because it is extremely bright. It's the third brightest object in our skies after the moon and the sun. And so it is photon rich. When a lot of the exoplanet work we're doing, we call it counting the photons because we only have like a handful of them. Venus is just showering us with photons every night. And so we have the ability to collect much more data in a variety of wavelengths. Now, most telescopes and instruments that are able to look at the right wavelengths can't take the intensity of Venus. It is too bright. So like JWST, extremely powerful, can't really look at Venus. It's too dangerous. And so for the machine, not for like life. And so we can look at Venus in other wavelengths. So that's part of my work. Some of it I erased from the board because it is not published yet. And so looking in the infrared is what I've been doing because phosphine has a lot of features in the infrared. Sadly, so do a lot of other molecules. And infrared light doesn't get through the clouds very well. It only gets the very cloud tops. And so it's very hard to see inside the clouds of Venus. So you can get more observational data at different wavelengths. You can get orbiters to fly around it and get better data from above and data that can tell us things like, does it change between night and day? Because any life that might be on Venus will be sensitive to the light from the sun. It's a source of energy. And so seeing diurnal and nocturnal variations is really important. Seeing how it changes across the poles and the equator and how it relates to how convection zones, Hadley cells work on Venus. So an orbiter will be really good for that. And we'll get one at the end of the decade with Da Vinci. And then because it is Venus, we can go in. Now, I feel very torn about the going in. I think because there's a chance there's life, we actually shouldn't necessarily go in. And when we go in, we need to be very careful with what we do. I think we are not good historically at going somewhere and treating it well. And so Venus will be no exception.
I was just going to say, I'm reading a world history of genocide right now. So what you just said rings very true to me at the moment. We do not have a good history of that.
No, and how tragic would it be that our first encounter with an alien life form would be to kill it, and that is very on brand, but I would like to not do that. And so I think because we can, going to Venus is extremely tempting and it would be so worthwhile in terms of scientific output, but we should consider it an ethically murky endeavor. But we can and we will go and sample it. And we have already thrown quite a lot of things at Venus, to be honest. Between us and the Russians, we've just been throwing things at Venus, and Venus has been able to defend itself very well. So I think it's okay-ish, but I feel very ethically conflicted about any in situ sampling. But when we do, we will know much more. We'll know exactly what is in the clouds, and we will have a much better starting point for figuring out what is there and what or who is producing it.
Okay. I'd like to finish with a few questions about space and exoplanets and the search for life beyond Venus. And returning to this issue of our work being done on Venus at the edge of instrument capabilities, would we be able to detect the phosphine in Earth's atmosphere from hundreds or thousands of light years away with the sorts of tools that we currently have? And the reason that this question comes to me is that if there's disagreement and difficulty surrounding detecting it on Venus, which is so comparatively close, I wonder how accurate our data and interpretations of the same are going to be for planets that are very, very far away.
It will be harder. It's absolutely true. So phosphine on Earth is at the parts per trillion, parts to quadrillion level. And there it's produced by life.
Magnitude there.
Exactly. And then we have parts per billion potentially on Venus. But Earth is not a place that phosphine feels welcome, because it's not a place where anaerobic life feels welcome. So it is reasonable to expect that a place that doesn't have oxygen, an exoplanet that doesn't have oxygen, would be able to have much more phosphine, more in the parts per billion or hundreds of parts per billion, 1 part per million, which...
That you're hoping for that.
And that we can detect. So the paper I naively published before the Venus story came out, where I was like, phosphine is great, you find it, it's life. But no. But that was specifically looking at that. Like, what is the minimum amount of phosphine that would have to be in an atmosphere for us to detect it with, say, JWST, which is already flying and collecting amazing data beyond its predicted capabilities. And so it required the right combination of planet and star, but I found many circumstances in which phosphine being produced at totally plausible quantities would be detectable with a telescope that already exists. Never mind the next generation telescopes that will come out in a few decades, within the next few decades, which are even better at looking at the components of atmospheres on exoplanets. That doesn't mean we can't look at a habitable, inhabited planet and miss it. But we are, for the first time, able to not miss it. And that is something to be celebrated, as long as we accept that it will be an uncertain and winding path. Except if we find CFCs, then that would be cool.
So oxygen, as we already touched on, though it is vital for our life, it is far from a surefire sign when found on another planet that life is present. But granted, this really big constraint, so there are thousands of gases out there that could be biosignatures, but there's this really serious constraint given that the spectra we have, or the gases for which we have the spectra, are a minority of those thousands. Are there other gases like phosphine that are close to surefire signs of life if they're found on planets that meet certain criteria, like being akin to the terrestrial planets like Earth, Mars, and Venus?
Only things like CFCs. There are no simple molecules, only because to be a good biosignature, you need to, yes, be produced by life, like water and methane. You need, or oxygen, molecular oxygen. You need to then have low false positives, and that's where things like phosphine and isoprene come in. They're produced by life, but also it's hard for non-life to make it. But the third kind of leg of this stool for life is it has to be detectable and distinguishable. So it needs to survive whatever atmosphere it's in and accumulate to detectable levels. So isoprene, low false positives for life. It is basically only produced by life. It is definitely produced by life, great, but it's really not detectable. It gets destroyed really quickly in almost any atmospheric circumstance we can throw at it. And so these are the three I play with. I think of all of those molecules and I think, okay, does life make it? Great. Well, can I see it if it's made? And would it have to be produced at quantities that are absolutely insane? Like everything on that planet has to be producing ethane to detect it. Then it's not a good biosignature, even if ethane can be produced by life. And so this is the three-pronged attack of how we defined whether a biosignature is good. Oxygen, very robust, but only in a very large context. Oxygen on Earth. If I was an alien astronomer looking at Earth and I found molecular oxygen at like a fifth of the atmosphere molecular oxygen on this planet around this sun, that would be a really good sign of life, because it is really hard to get oxygen in the context of our atmosphere with our trace gases, our oceans, and the radiation from our sun at this distance without life. So if I was an alien astronomer finding oxygen here, that would be very exciting. But that does not mean oxygen elsewhere is equally exciting.
Okay. Well, I hate to end on a perhaps sour note, but we have been fanboying and fangirling on Phosphine this entire time, which Phosphine totally deserves. I'm not going to take that away from Phosphine. But I'm wondering if Phosphine has any particular weaknesses that we haven't touched on. So I saw that because of its very high reactivity, it requires relatively high outgassing rates just to be detected. Is there anything else that hasn't come up in our conversation so far?
No, that's the game. The molecules are easy to detect, are easy to make. And so there's a very small window where they're just hard enough to make to be a good sign of life, but not so hard to make that you won't get enough of them to detect them. And so it's a really tough balance to strike for life, which is why life is hard to find. And that's okay. That's what the universe gave us. Probably a lot of very quiet life.
Okay. Well, Clara, this has been so fun, so informative. You really are an excellent advocate for quantum astrophysics and astrobiology, and I am so grateful for your time. Thanks for talking with me.
You're welcome. Thank you for your wonderful questions.
Hold on. If you haven't subscribed, liked, commented, or reviewed, that would be so helpful. And if you haven't yet, you could also follow me on Twitter and Instagram at Robinson Earhart.